All right, so this is part 2 to section 7.3, trig substitutions. So I've done one example, there are 7 examples in the book. I will probably do most of them just because this is something that is probably a little tricky for most people. So let's just jump in and do example 2 because I want to try and get at least 2 examples done per video. So we want to find the area enclosed by the ellipse x squared over a squared plus y squared over b squared is equal to 1. So you have to think back to the ellipse. So the way this is going to look is, so this is A, this is B, and yeah, that wasn't great. Try and draw this. We're going to need to do some logical reasoning here in a second. So obviously we haven't come up with a way of, finding this area of this closed curve, doing a simple integral. But one thing you'll notice is, if I just find the area of one of these, then just multiplying that by 4 will give me the answer. So when I'm trying to find this area closed, I can, just find the area under that, or this curve that I've just drawn an arrow to. I guess I can highlight it, this curve, then multiply that by 4, and that'll give me my answer. And if you know an answer going into a problem, that's even better. You can check your solution. The area of the ellipse is pi AB. The way to remember that is you know what the area of the circle is. It's pi r squared. Circle is an ellipse when a is equal to b is equal to r. So that's how I remember it, at least. All right, so we want to solve our equation here for y, and then we're going to find the area under that curve. So let's go ahead and do that. So we have x squared over a squared plus y squared over b squared is equal to 1. Multiply both sides by b squared. So I'm going to get x squared b squared over a squared plus y squared is equal to b squared. Y squared is equal to b squared minus x squared b squared over a squared. So let's do this. So we're going to factor out b squared over a squared. It's going to become a squared minus x squared here. You'll see why we do that in a minute. It's not completely necessary. It just makes the problem a little easier. All right, so let's go ahead and do this. So I'm going to get y is then equal to plus or minus the square root of b squared over a squared minus x squared. I'm going to take the positive root because I want positive root corresponds to the part of the graph I've highlighted in yellow. The negative would be the opposite of that. Negative would be this part that I'm highlighting now. We don't want that. Oops. Yeah, there we go. So take that, take the positive one. I'm going to pull the b squared over a squared out of the square root. So I'm going to get b over a, square root of a squared minus x squared. And so my area then is going to be 4 times, again, because I've only found 1/4 of it, because I'm only doing this part highlighted in yellow. It's going to be 4 times the integral from 0, and on the x-axis I stop at a, b over a, square root of a squared minus x squared. All right. So what we're going to do now is we can do a trig substitution. If you look at your table, you can figure out which one it is. The way I remember it is, I want a 1 minus signs. So I'm this minus sign here. So I want to be able to do a 1 minus sign squared there. So I'm going to let x equal a sine theta. Just like last time, dx will be a cosine theta d theta. So what I need to do now to make things easier on myself, I'm going to figure out, so I'm going to do, sorry, I forgot a dx on my integral. So I'm going to end up, so I'm going to need this anyway. So if I solve this first equation, x equals a sine theta for theta, I'm going to get theta is equal to the arc sine of x over a. Going to need that anyway, but you know, the difference between this question and last question is this is a definite integral. So in order to have to save myself from going back and, you know, drawing that triangle out, I had to do the last time to figure out, you know, what the arc sine of the cotangent of the arc sine was. If I do it this way, if I, you know, change my bounds using this, I can avoid that. All right, so let's jump into this. So my area then is going to be 4 times. I'm going to change my bounds. So I'm going to do theta. I'm going to look at theta of a and theta of 0. So a is my top bound. I plug it into theta. I'm going to get arc sine of a over a, arc sine of 1. And if I plug in 0, I'm going to get arc sine of 0. So arc sine of 1, what do I take what angle when I plug it into sine gives me 1? That's pi over 2. Arc sine of 0, same question. What angle do I plug it into sine gives me 0? It's going to be 0. My new bounds are now 0 to pi over 2. B over a, square root of a squared minus a squared sine squared theta. Yeah. And then I have a cosine theta d theta. Sorry, I didn't mean to make it all so bunched up. Let me copy it again down here. So just like U substitutions, I can change my bounds and it makes things easier. Using the substitution, I change my bounds. This way I won't have to go back and figure out what things are in terms of x. I can do this all in terms of theta now. Okay, so let's go ahead and do this integral. This is 4 times the integral from 0 to pi over 2. B over a. Pull an a out of the square root. I'm going to get a times the square root of 1 minus sine squared theta. A cosine theta d theta. So it's 4 times the integral from 0 to pi over 2. I have an a squared here. So I have b over a times a times a. So this is going to end up being, when I do all that simplification, ba times the square root of 1 minus sine squared theta. Use our identity. Cosine squared theta. So remember 1 minus sine squared is cosine squared. And then I have, so I've already simplified that a, cosine theta d theta. So just keep going. 4 times the integral from 0 to pi over 2. B, a square root of cosine theta is going to be cosine theta. I have 2 of those, so I'm going to get cosine squared theta here, d theta. B and a are constants. They are determined by the ellipse. This is 4ba, the integral from 0 to pi over 2, cosine squared theta d theta. And now we have to do this integral. And this was one of our integrals from the trig integral section. I think I might have been the first section of 7.1. You have to remember how to do this one. This is a really important one. Cosine squared theta is 1/2, 1 plus cosine of 2 theta. So I'm going to replace this 1/2, 1 plus cosine of 2 theta d theta. We're still going from 0 to pi over 2. Pull out the 1/2, I'm going to get 2ba. Sorry, my stylus wasn't drawing for a second. So 2ba, the integral of 1 plus cosine of 2 theta d theta. And now we're going to do this integral. So this is 2ba. Sorry, we're still going from 0 to pi over 2. And then I'm going to have the integral from 0 to pi over 2 of d theta plus the integral from 0 to pi over 2 cosine of 2 theta d theta. Clean up my work here so you can see what I'm actually talking about. All right, so let's do these integrals. This is 2BA. Integral d theta from 0 to pi over 2. This is going to be theta evaluated from 0 to pi over 2. Cosine 2 theta, if you need the u substitution, you can do it. This is going to be negative 1/2. Sorry, no negative. So positive 1/2 sine of 2 theta evaluated from 0 to pi over 2. So this is 2BA. Pi over 2 minus 0 is pi over 2. And then when I do this integral, I'm going to get 1/2 sine of pi minus 1/2 sine of 0. These are both 0. Sine of pi is 0. Sine of 0 is 0. So then this is 2BA times pi over 2. This is pi BA, just like we expected. Well, just like I expected. I don't think most of you guys have formula for ellipse memorized. I do, but it helps me. So that's that. So so again, it's, you know, we're gonna do same kind of deal every time. These take a little while to do, but they're good problems. It's all about it. So it's all about identifying, you know, what trig substitution am I going to make, and to identify that, I have to look at this, you know, this thing inside the square root, this a squared minus x squared, because it's in that form. I do this substitution, x is equal to a sine theta, figure out what dx is, and if it's a definite integral, then I want to figure out what theta is, because I want to change the bounds on my integral like I did on the part I just highlighted. So I change the bounds on my integral, plug everything in. It's a matter of simplification and integration using the techniques that we've already learned. So I'm going to stop that video there. These take a while to do. I don't want these all to be one example videos. I think I'll be able to fit 2 on the next one. So I'm going to stop here. So if you have questions, feel free to email me.